use the same water taxi problem that we talked about last class. Assume that the population of weights of men is normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. The A part of this problem is the exact same thing you were doing last night. Find the probability that if an individual man is randomly selected, his weight is greater than 175 pounds. First thing you're going to do on every problem, did I do it on this next slide? Yes. Whoops. You're going to draw a bell-shaped curve. You're going to put the mean, which was given to you as 172, right in the middle of that. You're going to say 175 would be to the right of the mean. And since you want the probability that his weight is greater than 175, the shading doesn't show up on here, but you would shade to the right of 175. Maybe on the slide that you have, you can go ahead and shade in to the right of 175. And then when using normal CDF, you're going to say, I'm looking for a probability or the area that starts at 175 and goes forever to the right. We're going to use 9,999 for that. Given that the mean is 172 and the standard deviation is 29. Put all four of those arguments in, hit enter, and you get about 46% or a probability of about 0.4588. Nothing different about that problem. That's the exact same thing we did last night. The probability that an individual would weigh more than 175 is about 46%. The probability that an individual would weigh less than 175 is about 54%. Here is the different part of the problem, though. The B part doesn't say find the probability that an individual man would weigh more than 175. It says find the probability that a group of 20 men would have a mean weight greater than 175. I'm just going to go out into the world, round up groups of 20 men, find the average of the group or the mean of the group. What's the probability that that mean will be greater than 175? I still use normal CDF. Greater than 175 would be 175 to 9,999. I still say the mean weight of men is 172, but I don't have the same standard deviation right there. The standard deviation in the previous slide was given to me as, what was it, 29? Yeah, 29. I don't have 29 right here because I'm not talking about the mean for an individual. I'm talking about the mean for a group of 20. And what the central limit theorem told me was that's when I have to adjust the standard deviation by dividing it by the square root of the sample size. So instead of having 29 right here, I have 29 divided by the square root of 20 because the sample size was 20. That's about 6.5-ish. When we do a problem that I can actually write on in just a second, I'll show you that you can actually type in 29 divided by the square root of 20 right there and not have to retype that digit. See you, Miss Tony. That's okay. That's all right. Not have to retype all those decimal places, which I think is what we're ready to do. Nope. Two more things. finishing up that example then, the probability that an individual weighed more than 175 pounds was about 46%. But in the B part, the probability that a group of 20 men would have a mean weight greater than 175 pounds was only about 32%. Here's the moral of this story. It's easier for an individual to deviate from the mean than it is for a big group to deviate from the mean. If we just took one professor from each university and we happened to pick a professor that had really, really low student evaluations, then we might think that whole university is bad because it's easy for one person to differ greatly from the mean. But instead of choosing one professor from each university, if we chose groups of 50 from each university, it would be a lot harder for the average of those groups of 50 to misrepresent the university than it would be if we just took one person to represent the university. It's easier for an individual to deviate for the mean than it is for groups of 20 or groups of 50 or groups of 1,000. The larger your sample size, the closer the average or the means will be to estimating the true mean of the population. All right. I think that's what the next slide says. Given that the safe capacity of the water taxi is 3,500 pounds, there's a fairly good chance with a probability of about 32% that it will be overloaded with 20 randomly selected men. Remember, the safe load of the water taxi was calculated 44 years before the sinking occurred, and the assumption was that the average man weighed 172 pounds. Well, if you let 20 people on, 20 guys on the boat at a time, there's about a 32% chance, or about 1 out of 3 times, the taxi would be overloaded. Because the probability that the group's average was more than the safe load is 0.3228. That wouldn't be good. 1 out of 3 times the boat's going to sink. That's not good at all. All right. Now we can do some examples on our own. And the homework will be assignment 16. So let's look at these other examples I have typed up. The first one is about SAT scores. If you're going to judge a high school by its SAT scores, and you just choose one student, that one student may or may not be very representative of the actual quality of the school. You might have gotten the brilliant student and everybody else is not that bright. Or you might have gotten the not so bright student when everybody else is very gifted. So this is 2 different situations. The A part is if one SAT score is randomly selected, what's the probability that that one is between 1440 and 1480? And the B part is, what if instead of using one student to represent the school, I use 16 students to represent the school? Then that would probably be a more accurate reflection of the scores of the entire student population than just using one score would be. So, assume SAT scores are normally distributed with a mean of 1,518 and a standard deviation of 325. If one score is randomly selected, Find the probability that it's between 1440 and 1480. We can use the same picture for both of these. Here's the normally distributed SAT scores that have a mean of 1,518. And both of the scores that we're interested in are below the mean, 1440 and 1480. We're looking for the probability in the A part that an individual score lies in that range. And in the B part, the probability that the mean of a group of 16 falls in that range. For both of them, I'm going to use, since I'm looking for a probability, I'm going to use normal CDF. It's not binomial because there's not only two outcomes for what's your SAT score. I'm going to use normal CDF. And what's the first thing I need to enter? I'm looking for the probability that an individual score lies between what? 1440 and 1480. If I close my parentheses right now, the calculator will assume that the mean SAT score is 0 and the standard deviation is 1. That's not true at all. So I have to follow up with what the mean SAT score is and the standard deviation. I got that to be about 0.0483. Anybody second that? In other words, there's about a 5% chance that a randomly selected individual would have an SAT score between 1440 and 1480. Let's find the probability not just for an individual, but in the B part, the probability that a group of 16 would have an average or a mean between 1440 and 1480. Here's what you have to watch out for on the test. Does the problem say individual or group? If it says group, then you have to train your brain to think, oh, that's when I need to adjust the standard deviation. I'm not just going to use 325, but I'm going to use 325 divided by the square root of the sample size, which is in this case 16. You can either calculate, that's supposed to be sigma, it kind of looks weird. You can calculate the standard deviation of the sample means by taking the population standard deviation and dividing it by the square root of the sample size. I got that to be 81.25. And since that doesn't have too many decimal places, it would be easy to type in the same thing I did in number 8, but instead of using 325 for the standard deviation, use 81.25. That's one way I could do it. Or I could let the calculator, I have to double check this, but I think it works. I could let the calculator find the standard deviation of the sample means right in the body of this argument. Somebody punched that. I believe it comes out to be 0.1515. So you can either calculate this and then retype it, or you can just let the calculator do the calculation inside the parentheses. It works either way. Square root is second and then your square button. No, the square root first. This calculator, everything is wonderful left to right. So square root and then 16 and then close parentheses and then equals. I think it's even okay if you forget to close the parentheses. Is anybody having any trouble getting that? Did it work for you? Okay. Anybody having any trouble, or you've got one of the calculators that looks slightly different? What is the one word that you're looking for on the test that's going to tell you, oh, I have to adjust the standard deviation? Group. It's that easy. If you realize group means I have to adjust the standard deviation, then it's just like last night's homework. The C part says, why can the sample limit, or why can the central limit theorem be used in part B even though the sample size does not exceed 30? I actually forgot to ask myself, can I use the central limit theorem? I just did. But if I had been thinking like I should have been, I would have said, hey, that sample size is less than 30. I may not be able to use the central limit theorem. The central limit theorem is what told us just to adjust the standard deviation and then play like it's a normal. Why could I use the central limit theorem even though that sample size was less than 30? Because I was told in the beginning if it's normally distributed. If I didn't know that the population was normally distributed, then what I did in the B part would be invalid unless the sample size was greater than 30. But if the sample size is greater than 30, then it doesn't matter whether your sample is normally, or your population is normally distributed or not. You say not enough information? Or you mean not normally distributed and sample size less than 30? Yeah. Then you have to say, I don't know, central limit theorem doesn't apply. That's not going to happen. That's not going to happen, but you do need to be aware of those two conditions. Either you have to know that the population is normally distributed, or you have to know that your sample size is greater than 30, and then it doesn't matter whether or not your population is normally distributed.